What is the largest number that humanity has ever conceived of? There is, of course, no largest finite number. If you choose any value of n, well, I can just choose n plus 1, and my n plus 1 is bigger than your n. But there's still many interesting questions here, like what's the largest number ever used in the middle of a mathematical proof? Or the largest number that represents some mathematical pattern, or just the largest number that humans have ever managed to invent or discover. So in this video, we're going to open the door just a crack and peek into the bizarre world of Googology, the study of unfathomably large numbers. My thanks to Brilliant for sponsoring this video. More about them at the end of the video. Let's begin our journey with this particular number. This is the largest power of 10 that I was able to fit on my 1080p screen, or at least the largest one that I could fit at this font size. If I made the number smaller, for example, I could imagine fitting this number, which is a 1 followed by 100 zeros. So if I want to construct the largest number possible, I'm going to really quickly run into a problem doing this way, which is I'm no longer going to be able to visualize it on my 1080p screen. Thankfully, mathematics have a notational trick that allows us to deal with really long numbers like this much more efficiently. This is just 10 to the power of 100, infamously known as 1 Googol. Just to give one sort of bizarre physical interpretation of how big this number is, if you took the entire universe and you filled the entire universe with sand, then it would take about 10 to the 90 particles of sand to fill up the entire universe. So this number is even bigger than that. But the real point here is that because we've introduced this exponential notation, 10 to the power of 100, with the screen real estate that I have, it's easy for me to go bigger than that. For example, another famously large number is referred to as the Googolplex, and a Googolplex is just 10 to the power of a Googol. And okay, what was a Googol? A Googol was 10 to the power of 100, and it's sometimes nice to write this as 10 to the 10 to the 10 squared. Now, this number I can't even really faithfully call astronomically large. For just a Googol, I had some sort of astronomical universe scale comparison, but a Googolplex is so much larger, one with a Googol zeros behind it, that I don't really have any meaningful physical way to describe this. It's just unbelievably large. It still is going to be kind of trivial in comparison to the numbers that we're going to see later in this video. Because as soon as I look at it this way, 10 to the 10 to the 10 squared, I think, well, I can use that trick of exponents over and over and over again. How about something like this one? 10 to the 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 10, until I again run out of screen real estate. I mean, this number is just vastly larger than a Googolplex, because a Googolplex was only 10 to the 10 to the 10 squared. That was it. This, of course, is just unfathomably larger. I'm running out of new vocabulary. I can't use astronomical. I don't know what other words in the English language to describe just how much bigger this is than a Googolplex is. And if you want, you could do the same kind of thing. What about a Googolplex to a Googolplex to a Googolplex? Again, the limit is my screen real estate. Now, the thing I really want to observe here is that I'm constructing larger and larger numbers, but I'm still using the basic idea of exponents, and that idea is getting a little bit tired. Like a Googolplex to the Googolplex to the Googolplex to the Googolplex. Yes, it's enormous, of course, but I haven't really come up with a novel idea. So now I want to show you a new type of notation that, much like exponents, allows us to talk about things that are incredibly large, but larger in a way that exponents can never even begin to touch. This is Knuth's up arrow notation. Here's how it works. I want to begin with multiplication, say 2 times 4. What really is 2 times 4? Well, 2 times 4 is 2 plus 2 plus 2 plus 2. There's 4 copies of addition. So when I think about what multiplication is just really repeated addition. And then, okay, well, what about exponentiation? So 2 to the power of 4, this is 2 times 2 times 2 times 2. 4 copies. That is, exponentiation is repeated multiplication in the same way that multiplication is repeated addition. In fact, you could even go one step further. What about just plus 4? Well, plus 4 is kind of like plus 1 plus 1 plus 1 plus 1. 4 copies of plus 1, which we could call incrementation. So our operations are sort of repeated incrementation, repeated addition, repeated multiplication. You can probably guess what's next. It's going to be repeated exponentiation. But before I do that, I wanted to introduce a new piece of terminology, a new notation. Instead of 2 to the 4, I'm going to call it 2 up arrow 4. A single up arrow here just refers to taking the exponent. And I'm going to introduce this symbology here now so that I can talk about double up arrow notation, 2 double up arrow 4, which is a power tower. 2 to the 2 to the 2 to the 2, 4 copies in that tower. This fourth operation in my hierarchy of repeated incrementation, repeated addition, repeated multiplication, and now finally repeated exponentiation is called tetration. And the way I can understand this a little better than maybe just my power tower is this is like taking 2 to the single up arrow 2 to the single up arrow 2 to the single up arrow 2 again 4 times. In this case, single up arrow is just exponentiation, and so I get that sort of power tower. Now, I want to note one little technicality. I have this power tower here, and I haven't put any brackets in. But the implicit way that I'm interpreting brackets is I work right to left, or from the top of the tower down. That is, at the top of the tower, the top 2 squared, I'm going to say this is 2 to the 2 to the, well, 2 squared is 4. 2 to the 4 is 16, so I can replace this. And then 2 to the 16, well, the computer science majors might recall it's 65,536. Now, we haven't gone very far yet to double up arrow 4, and already we're at a number in the tens of thousands. But let's take the same trick and let's just do it one more time. Let me talk about triple up arrows now. Okay, to triple up arrow 4 is to double up arrow 2, double up arrow 2, double up arrow 2, as in 4 copies of 2 with double up arrows in between them. So the natural extension of the previous thing. Okay, so what is this number? Well, again, let's work right to the left. So let's focus on the 2 double up arrow 2 on the right-hand side. So double up arrows refer to power towers. This is a power tower with a base of 2 that gets repeated, and it gets repeated 2 times. So this is just 2 to the 2. So if I plug that in, I get in that spot 2 to the power of 2, and 2 to the power of 2, of course, is just 4. Okay, now I'm going to focus on, again, the right-hand side. 2 double up arrow 4, well, that's the thing we just computed, right? That was the 65,536. So, but what is that? Well, double up arrow refers to power towers, right? It refers to these iterated or repeated exponentiations. So this is like 2 to the 2 to the 2 to the 2 to the 2, 65,336 times. It's an enormously large power tower. Now, remember the 10 to the 10 to the 10 example that kept on going until I ran out of space on my screen? Well, I don't want to write down 2 to the 2 to the 2, 65,536 times. I'm not Mr. Beast. And so there's no reasonable way to express this without just taking an enormous amount of time. But this new notation to triple up arrow 4 allows us to write it in a nice, very short, concise way. And if you just try and pause and think how outrageous this number is, well, it's going to sort of be hard to wrap your mind around it. I mean, just 2 to the 16, that would be, 16 2s in the tower, was already 65,000. That's just 16 of them. Now you have 65,536, and every time you add 1 to it, you're taking 2 to the whole power of everything else you had before. And really, there's no way, at least for me, to even just wrap my mind around how outrageously large a number like this is. And this new notation that I've introduced has just given me an avenue to be able to explore this. Now, this notation is used in one specific example that's incredibly infamous and really got the Googology ball rolling, which is Graham's number. And I really wanted to go and explain what this is. So the idea is I want to start with 3 quadruple up arrow 3. You can pause for a moment and think in comparison to what we did. Okay, this is now 4 up arrows, not 3. And instead of having a root of 2 for all the power towers, it's a root of 3. This number already is just unfathomably large. Again, I have no vocab in my vocabulary to be able to express how ridiculous this number is. We're just getting started. So next up, let's do g of 2. I'm going to imagine a sequence, g1, g2, g3. Graham's number itself is going to be g of 64. So g of 2 is 3, and then the number of up arrows is g of 1. That's just crazy. So already we had seen previously that 3 up arrows was outrageous. Now we're saying we take that outrageous number, this even larger one, this g of 1, and that's just the number of up arrows that you have. And you can keep on going. G3 would be like 3, and then the number of up arrows would be the previous state, the Graham's number of 2, and so forth. And we're going to keep on going all the way to G of 64. So this is a 3 with G of 63 up arrows. What is going on here? That is actually Graham's number. Now, I mean, you could choose something else, G of a Googolplex or something like this. But this specific number, G of 64, was actually used in an actual mathematical proof. Now, I'll link down in the description to a number file video with the actual creator of this number who describes the actual problem that this was meant to be used. But it got such infamy because it was this, again, just unfathomably large number. And I really do encourage you to pause and try to reflect on how big this is. But this unfathomably large number that was actually used in a mathematical proof to provide an upper bound for something actually in graph theory, a portion called Ramsey theory. Again, you can check it out. I won't cover that in this video. So there's actually something mathematical that this just unbelievable number is useful for finding an upper bound for. But as big as this is, it isn't the largest of the big, famous, unbelievably large numbers. And for the next one, I want to show you something that doesn't come from notation, that instead comes from a simple problem in graph theory. So here's the idea. I want to begin with something called a tree. So this is a tree. It's got a bunch of nodes. There's a specific node at the base of it, at the root of it, and then everything sort of branches up from there. Additionally, I can imagine these nodes have different colors. So this is a tree with, 6 different nodes, but 3 different colors that can color code those nodes. And what I want to do is I want to create a sequence of trees. A first tree, a second tree, a third tree, and a fourth tree, and so on. But my sequence of trees has to obey certain rules. So the first rule is this. The kth tree in my sequence can have at most k nodes. So here's an example. I could have, for example, the first tree is just, you only have 1 node. That's all I can do, a single node. The second tree could have 2 nodes. The third tree could have 3 nodes. The fourth tree, again, it says at most k nodes. So the fourth tree, which in my picture here only has 2 nodes, well, that's at most 4 nodes. 2 is less than 4. So this is the type of idea of a sequence of such trees. That's the easy condition. Here's the other rule that I'm going to have. You're making this sequence of trees. It has this condition on the number of nodes you can have. It also has this next condition. It says no previous tree in the sequence is embeddable into the current tree. Okay, so what do I mean by this condition? I'll try to describe it. So imagine I have, for example, how about this one? This is just a tree that's just got a single thing. And then I have this more complicated tree. If I look at the more complicated tree, if I just look at the base, I'm like, okay, there's a single yellow node there. And I can kind of imagine that the single node I began with is embedded into the larger tree. This situation is not allowed. That single node got embedded into the larger tree, not allowed in my sequence. Okay, let me do another scenario. Now I have this, slightly more complicated tree that's got 3 different components. But again, if I look at my bigger tree, it just looks like it's identical in there. I can sort of imagine taking the tree and embedding it directly in. Not allowed. And then the third example is a little bit more complicated. Okay, in this one, I've changed the colors of my first tree. It's got 1 green and 2 yellows. And in particular, the top 2, their common base is yellow. But if I look at the tree on the right now, well, the top I've got a green and a yellow as well. It's more complicated, but if I ask the question of what is their common ancestor? Common ancestor means you go down the tree until you find that base where it finally, that's splitting. Their common ancestor at the bottom is yellow. And this is, again, a not allowed embedding. I can take those 3 points, I can embed them in this way. Again, this is not allowed. So I'm making the sequence of trees, and I have to make sure both of these 2 rules are embedded. Finally, here's the definition of my number. Tree of n is defined to be the longest sequence that I can construct using only n different colors to label my nodes. Okay, so let's just play around. Let's try to compute tree of a bunch of different numbers. So let's do tree of 1 first. So this is allowing 1 different color. Okay, first tree is allowed to have 1 node. I'll make it say blue. Now, the second tree is allowed to have up to 2 nodes, but it has to not be able to be embedded. But I've only got 1 color, so the only option would be like maybe just 2 blues, but then the single blue definitely embeds into this, so this is absolutely not allowed. There's only, in the end, one possible tree in this sequence, so tree of 1 is 1. Okay, let's do tree of 2 now. So I'm allowed to have 2 different colors. First tree in my sequence can only have 1 node. I'll just arbitrarily choose it to be blue. Now for the second tree, you're allowed to have either 1 or 2 nodes in it. And I could just choose the other color. But then it occurs to me that if I use up the 2 colors as single nodes, there's nothing that I can have for the third tree because it couldn't have either of the 2 colors. So to try to get the longest possible sequence, what I'm going to do for my second entry is take 2 different yellows that are connected. So this is a different color, right? There's no embedding. The blue can't be embedded into here. And what's relevant is now I can try and think about what a third tree would be possible. Okay, it can include a blue, and it can't include 3 yellows in a row because the 2 yellows would just embed in it. But remember, it was at most 3 nodes can be in the third tree. Well, I could therefore do less. For example, I could go down just to 1, and this is allowed. But then, sadly, nothing else is allowed, and so tree of 2 is just 3. I mean, I can't have any more blues, I can't have any more yellows. That's just it. These are the only 3 options. So tree of 1 was 1, tree of 2 is 3. Let's do tree of 3 now. This one is going to be crazy. Okay, I mean, I get to do a lot of different ways, and you can try your own sequences here. I'm just going to do one possible one. I'm going to start with the blue one as I've done before. I can never use blue again because this could be embedded in. Then I'm going to do, I don't know, 2 green ones, say. There's lots of different options you can try choosing. And then, okay, for the third one, I just have to have something that doesn't have 2 greens side by side. So how about like green, yellow, green? There is the 2 greens in here, but their common ancestor is yellow. And so that didn't occur in my step 2. So this is allowed. And I can just keep on going this way. There's so many different options. Again, I really encourage you to actually to pause the video and try to play around and come up with a bunch of these sequences. It's really fun to do. And what you'll notice is it's possible to get sequences that start being incredibly, incredibly, incredibly long. And it's always possible to keep on adding things. And I know I've only put 7 here, but it can go unbelievably large. Actually, you then have a question. Well, hold on, maybe tree of 3 is infinite because you're not going to have problem adding new things to this. So you might be like, well, maybe tree of 3 is infinite. There's enough freedom, there's enough flexibility. This is an infinite number. Well, shockingly, it has been proven that tree of 3 is both a finite number, but also unfathomably large. For example, it makes Graham's number look just completely trivial in comparison. This is one of the largest numbers that we can conceive of that actually represents like this relatively simple and easy to state problem in graph theory. Now, there is, of course, more to say beyond tree of 3, as unbelievably large as it really is. You could check out, for example, the Googology wiki, where it shows this entire listing of some of the unbelievably large numbers that people have come up with. Now, if you want to learn more cool mathematics, I'm very proud to share the sponsor of today's video, which is Brilliant. Brilliant.org has an enormous number of courses for subjects in mathematics, physics, and computer science. For example, if you enjoyed this video, you might enjoy some of their lessons introducing graph theory or going beyond finite numbers to crazy puzzles when you take limits as things go to infinity. But what I really appreciate about Brilliant is how so many of their lessons are interactive and visual. For example, take the Pythagorean formula, a squared plus b squared equal to c squared, a basic fact that lots of people just have to memorize in all of their math courses. But do you know why the Pythagorean theorem is true? Can you visualize how the proof goes in your mind? Check out just how beautifully Brilliant treats this. Their entire lesson on the Pythagorean theorem is full of these beautiful interactive elements where you can visualize exactly what's going on in the proof. You get to test yourself. For example, I can figure out that the area of the outer square here is going to be 2ab plus c squared. Let's see if I get that correct. I do, yes. And as you go through this proof and checking out the different visual elements, you start to understand exactly why the Pythagorean theorem is true. For example, as I drag the sliders here, I can see how the different relevant rectangles in the proof of the Pythagorean theorem are going to change. And it just lets me build this perfect visual intuition for why this proof actually works. This kind of active learning is so important for deep understanding the material and long-term retention, and it's why I'm so proud to be sponsored by Brilliant. So go to brilliant.org/Trevor Bassett, sign up for free, or the first 200 people who use the link down below to sign up are going to get 20% off an annual premium subscription. And with that said, if you have any questions about these crazy large numbers, feel free to ask down in the comments below, and we'll do some more math in the next video.